Everything you've ever seen, every star in the night sky, every planet, every galaxy, every nebula, every single bit of matter that we can observe and measure and touch and detect, represents only about 5% of what actually exists in the universe. 5%. The rest, the overwhelming majority of the universe, the other 95%, is made of stuff we cannot see, stuff that doesn't emit light, stuff that doesn't absorb light, stuff that doesn't interact with light at all. And yet, this invisible stuff is absolutely essential. Without it, galaxies wouldn't exist, stars wouldn't have formed, you wouldn't be here. Tonight, I want to take you on a journey to understand one of the most profound mysteries in all of science. Dark matter, the invisible mass that holds galaxies together, the hidden scaffolding of the universe, the stuff that makes up about 27% of everything that exists, but that we've never directly detected. When you understand what dark matter is, or more accurately, what we know about what it might be and what it definitely does, it changes everything. It changes how you see the universe. It changes how you understand reality itself. Because we're living in a cosmos where most of what exists is invisible to us, where the architecture of reality is built from something we cannot see, where galaxies are held together by gravitational forces from matter that doesn't shine. This isn't science fiction. This isn't speculation. This is the reality we live in, confirmed by decades of observations and measurements. And it should absolutely blow your mind, because we're going to explore the invisible universe together. We're going to understand how we know something we can't see exists. How we figured out that most of the universe is made of something completely different from everything we've ever touched. And why this invisible matter is the reason you're alive to hear these words. Before we dive into dark matter itself, I need you to understand just how little of the universe is made of regular matter. The stuff we call regular matter, or baryonic matter in physics terms, is everything made of atoms, protons, neutrons, electrons, the periodic table, everything you've ever interacted with, your body, the air you breathe, the earth beneath your feet, the sun, the stars. All of it is regular matter, and this makes up about 5% of the universe. 5%. Now, when I say that, your brain might not immediately grasp how shocking this is, so let me put it in perspective. Imagine you're looking at the ocean. You see the water, you see waves, you might see some boats or marine life. That's what you can observe. But now imagine that what you're seeing, all that water, all those waves, everything visible, is only 5% of what's actually there. The other 95% of the ocean is made of something completely invisible that you cannot detect with your eyes or any normal instruments. But this invisible stuff has mass. It has gravity. It affects how the visible water moves. And without this invisible stuff, the ocean couldn't exist in the form you see it. That's our universe. Everything we've ever observed, every galaxy we've photographed, every star we've studied, every planet we've discovered, all of it is just the tiny, visible portion floating in a vast sea of invisible matter and energy. And the invisible matter, the dark matter we're talking about tonight, makes up about 27% of the universe. That's more than 5 times more than all the regular matter combined. For every atom in your body, There are roughly 5 times as many dark matter particles passing through you right now. You're surrounded by it, immersed in it, and you can't feel it, can't see it, can't detect it with any of your senses. But it's there. We know it's there, and we're going to explore how we know, what it does, and why it matters. Now let me tell you how this all started, because the story of dark matter's discovery is one of the most fascinating tales in modern science. It begins in 1933 with a Swiss astronomer named Fritz Zwicky. Zwicky was studying the Coma Cluster, a large collection of galaxies about 300 million light-years from Earth. He was measuring how fast these galaxies were moving, watching them orbit around their common center of mass. And he noticed something strange. The galaxies were moving way too fast. Let me explain why this was a problem. When you have a bunch of objects held together by gravity, like galaxies in a cluster, there's a relationship between how fast they can move and how much mass is holding them together. If they move too fast, they should fly apart. Gravity wouldn't be strong enough to hold them. Think of it like spinning a ball on a string. The faster you spin it, the stronger the string needs to be to keep the ball from flying away. If you spin it too fast, the string breaks and the ball goes flying. Galaxies in a cluster are similar. They're held together by the gravitational pull of all the mass in the cluster, and the more mass there is, the faster the galaxies can orbit without escaping. Zwicky measured the speeds of the galaxies in the Coma Cluster. Then he calculated how much mass should be there based on the visible galaxies, the stars he could see. And he found a huge problem. The galaxies were moving so fast that they should have flown apart long ago. The visible mass wasn't nearly enough to hold them together. In fact, he calculated that there needed to be about 400 times more mass than what he could see to keep the cluster gravitationally bound. 400 times more. This was insane. Where was all this mass? Zwicky called it dark matter. Matter that was there but that didn't shine. Matter that had gravitational influence but that wasn't visible. And here's the thing. Almost nobody believed him. For decades, his observations were largely ignored. People thought he must have made a mistake. Maybe his measurements were wrong. Maybe he was misunderstanding something. Because the idea that most of the mass in the universe is invisible, that it's made of something completely different from normal matter, that was too radical, too strange. It couldn't be right, except it was. But it would take another 40 years before the evidence became so overwhelming that the scientific community had to accept it. And that acceptance came largely from the work of one remarkable astronomer named Vera Rubin. Vera Rubin, working in the 1970s, was studying how galaxies rotate. She was measuring the speeds of stars at different distances from the centers of galaxies. And what she found revolutionized our understanding of the universe. Let me explain what she expected to find and what she actually found, because the difference is crucial. Think about our solar system. The sun is at the center and contains almost all the mass. The planets orbit around it, and there's a simple relationship. The farther from the sun you are, the slower you orbit. Mercury, close to the sun, zips around in just 88 days. Earth takes 365 days. Jupiter, much farther out, takes almost 12 years. Neptune, at the edge, takes 168 years. The farther you are, the slower you go. This makes sense. The sun's gravitational pull gets weaker with distance, so objects farther away feel less pull and orbit more slowly. This is basic physics. Kepler figured this out in the 1600s. Newton explained why with his laws of gravity. It's one of the fundamental patterns in the universe. Vera Rubin expected galaxies to work the same way. She expected that stars close to the galactic center would orbit quickly because that's where most of the mass is, where most of the stars are concentrated. And stars farther out, on the edges of galaxies, should orbit more slowly as the gravitational pull weakens. But that's not what she found. Not at all. The stars at the edges of galaxies were moving just as fast as stars closer to the center. In some cases, even faster. The rotation curves, the graphs showing orbital speed versus distance from the center should have dropped off. They should have declined, but they stayed flat. Stars at the edge were whipping around at hundreds of kilometers per second, way faster than they should be if only visible matter was present. This made no sense. According to everything we understood about gravity, these outer stars should have been moving slowly, or they should have been flung out of the galaxy entirely by centrifugal force. But they weren't. They were held in, moving fast, stable. Something was holding them, something with gravity, something with mass. But this something wasn't visible. It wasn't the stars, it wasn't gas or dust, it was something else. And it wasn't just one galaxy. Rubin studied dozens of galaxies. And they all showed the same pattern. Flat rotation curves, stars moving too fast at the edges. Every single galaxy seemed to be surrounded by a massive amount of invisible matter. Matter that extended far beyond the visible disk of stars. Matter that provided the extra gravitational pull needed to keep those outer stars from flying away. The only way to explain what she was seeing was to accept that galaxies are surrounded by halos of dark matter. That visible matter, the stars we see, is just the tip of the iceberg. That the bulk of a galaxy's mass is this invisible stuff spread out in a vast halo surrounding and permeating the visible galaxy. And this wasn't a small correction. The amount of dark matter needed to explain the observations was enormous, roughly 5 times more dark matter than visible matter in a typical galaxy. 5 times more of something we couldn't see than of everything we could see. This was Zwicky's missing mass all over again, but now with much more detailed observations. Now with measurements that couldn't be easily dismissed. And slowly, over the course of the 1980s and 90s, the scientific community came to accept it. Dark matter is real. It exists. We don't know what it is, but we know it's there. And we know that without it, galaxies as we know them couldn't exist. Now I need to tell you what dark matter isn't, because there are a lot of misconceptions and a lot of ideas that have been proposed and ruled out over the decades. When scientists first started taking dark matter seriously, the natural question was whether it could be regular matter that just isn't shining. Maybe it's planets, rogue planets that aren't orbiting stars and so don't reflect light. Maybe it's asteroids and comets, small objects scattered throughout space. Maybe it's dead stars, white dwarfs or neutron stars or black holes. objects that were once stars but have burned out and are now dark. Or maybe it's dust and gas that's too cold to emit much light. All of these ideas fall under the category of MACHOs, which stands for Massive Compact Halo Objects. Objects made of regular matter that happen to be dark. And scientists looked for them. They conducted surveys. They searched for gravitational lensing effects, the bending of light from background stars by dark objects in the foreground. They looked for black holes. They studied star populations to estimate how many dead stars there should be. And here's what they found. There just isn't enough. Even if you add up all the possible dark regular matter, all the planets and asteroids and dead stars and dust and gas, you don't get anywhere close to the amount of dark matter needed. Not even close. You might account for a small fraction, maybe 10 or 20% of the dark matter, but that's it. The rest has to be something else. Something not made of atoms. Something that isn't baryonic matter. And here's the key thing. Dark matter, the real dark, matter that makes up most of the missing mass, doesn't interact with light at all. It's not just dark in the sense of not emitting light. It doesn't absorb light either. It doesn't scatter light. Light passes through it as if it's not there, which means it's not made of protons, neutrons, and electrons. It's not atoms. It's something completely different, something that only interacts through gravity, and maybe through the weak nuclear force, though we're not sure about that. This is why we can't see it. It's not that it's hiding in dark places. It's that it's fundamentally transparent to electromagnetic radiation. Photons don't bounce off it. Photons don't get absorbed by it. Photons just ignore it. The only way we know it's there is through gravity, through its gravitational effects on things we can see, the rotation curves of galaxies, the motions of galaxy clusters, the bending of light from distant sources. All of these are gravitational phenomena, and they tell us that there's mass there, lots of mass. But this mass is not interacting with light in any way. So, if dark matter isn't regular matter, what is it? What are the leading theories for what this stuff actually is? Well, the honest answer is we don't know, but we have ideas. The most popular idea, the one that's been the leading candidate for decades, involves particles called WIMPs. That stands for Weakly Interacting Massive Particles. The idea is that dark matter is made of a new type of fundamental particle that we haven't discovered yet. A particle that has mass, so it has gravity, but that doesn't interact with electromagnetic force, so it doesn't interact with light. The weak interaction part refers to the weak nuclear force, one of the 4 fundamental forces in physics. Some theories suggest these particles might interact through the weak force, which would make them extremely hard to detect, but not impossible. The massive part means they have significant mass, maybe 10 to 100 times the mass of a proton. WIMPs come out of theories in particle physics that extend the Standard Model, the theory that describes all known particles and forces. Theories like supersymmetry predict that for every known particle, there should be a heavier supersymmetric partner, and one of these partners, maybe the neutralino, could be stable enough to be the dark matter particle. The math works out. The predicted abundance of these particles, if they exist, could match the amount of dark matter we observe, and they would have exactly the properties we need. Mass for gravity, No electromagnetic interaction, possibly weak force interaction. For years, WIMPs were the favorite. Scientists built incredibly sensitive detectors deep underground to shield from cosmic rays, trying to catch a WIMP colliding with an atomic nucleus. But so far, after decades of searching, we haven't found them, which doesn't mean they don't exist. It might mean they interact even more weakly than we thought, or it might mean we need to look in different ways. But it has led to other ideas gaining attention. Another candidate is the axion. Axions are hypothetical particles that were originally proposed to solve a problem in particle physics called the strong CP problem. The fact that they could also be dark matter is almost a bonus. Axions would be much lighter than WIMPs with very tiny mass. But there would be an enormous number of them. They'd be everywhere, passing through everything constantly. And they might interact very weakly with photons under certain conditions, which could make them detectable. Experiments are underway to search for axions. They're different from WIMP detectors. They look for the tiny interactions between axions and magnetic fields, and some recent results have been intriguing, though not yet conclusive. Then there are even more exotic ideas. Sterile neutrinos, primordial black holes. Dark matter might not even be particles in the traditional sense. It might be some kind of field, or it might be something we haven't thought of yet. The truth is, we're still searching. We have constraints. We know dark matter has certain properties based on how it behaves in galaxies and clusters. It has to be cold, meaning it moves slowly compared to the speed of light. It has to be stable, not decaying quickly. It has to be abundant. But within those constraints, there's a lot of possibility space. A lot of different things dark matter could be. And we won't know until we detect it directly, or until we develop theory that makes a clear, testable prediction. The search for dark matter particles is one of the major endeavors in physics today. Experiments underground, experiments at particle colliders, experiments in space, all trying to catch a glimpse of what the universe is mostly made of. Let me now take you deeper into why we're so confident dark matter exists, even though we've never detected a dark matter particle, because this is important. Some people hear that we haven't found dark matter particles and they think maybe it doesn't exist. Maybe we're wrong. Maybe we're misunderstanding gravity. And that's a fair question to ask. Maybe our theory of gravity, general relativity, is incorrect on large scales. Maybe we need a modified theory that explains the rotation curves without dark matter. This idea is called MOND, Modified Newtonian Dynamics, and its various relativistic versions. And scientists have explored this. Seriously, because it's important to consider alternatives. But here's the thing. The evidence for dark matter doesn't come from just one source. It comes from many independent observations, and all of them point to the same conclusion. There's invisible mass out there. Let me give you some examples. First, there are the galaxy rotation curves we talked about. Flat rotation curves that indicate dark matter halos. But that's just the start. There's the bullet cluster. This is one of the most compelling pieces of evidence. The bullet cluster is actually two galaxy clusters that collided with each other. When they collided, the galaxies themselves mostly passed through each other because space between stars is so vast. But the hot gas that fills galaxy clusters, the intergalactic medium, it collided and interacted. The gas in one cluster slammed into the gas in the other cluster. This gas is visible in X-rays. We can see where it is, and it's in the middle where the collision happened. But here's the key. When we measure where the mass is, using gravitational lensing, the bending of light from background galaxies, we find that most of the mass isn't where the gas is. Most of the mass is where the galaxies are. The dark matter passed right through with the galaxies. It didn't interact and slow down like the gas did. This is exactly what you'd expect if dark matter is collisionless. If it only interacts through gravity, if it doesn't interact with itself or with regular matter through any other force. The bullet cluster shows us visually through lensing maps where the invisible mass is, and it's not where the visible mass is. You can literally see the separation between visible and dark matter in this collision. It's stunning. Then there's the cosmic microwave background. This is the radiation left over from the Big Bang, from when the universe was about 380,000 years old. The patterns in this radiation, the tiny temperature fluctuations, tell us about the composition of the universe, and the data fits perfectly with a universe that's about 5% normal matter and 27% dark matter. The precise ratios come out of fitting the observations to cosmological models, and they work. The predictions match the observations to incredible precision. There's also large-scale structure, the distribution of galaxies in the universe, the cosmic web. Galaxies aren't randomly distributed. They're organized into filaments and clusters and voids. And simulations show that this structure can only form if dark matter exists. If you run a simulation with just normal matter, you don't get the structure we see. But if you include dark matter, which forms a scaffolding, a framework that normal matter falls into, you get exactly the patterns we observe. All of these different lines of evidence from completely different types of observations all point to the same thing. There's extra mass, invisible mass, dark matter. It's not one observation that could be explained away. It's not one anomaly. It's a consistent picture from multiple independent sources. And that's why the scientific community is so confident dark matter is real. Even though we haven't found the particle yet, we know it's out there. We can see its effects everywhere we look. Now let me tell you what dark matter does, why it's so important, why it's not just some curiosity, but actually essential for the existence of everything we see. Because dark matter isn't just extra mass sitting around doing nothing. It's the foundation of cosmic structure. Without dark matter, the universe would look completely different. In fact, without dark matter, galaxies probably wouldn't exist at all. Here's why. In the early universe, just after the Big Bang, matter was almost perfectly smooth. Almost. There were tiny density fluctuations, tiny variations in density from place to place. These came from quantum fluctuations in the very early universe, stretched to cosmic scales by inflation. But they were tiny, about 1 part in 100,000, barely noticeable. Now, these tiny fluctuations, these slight overdensities and underdensities, are the seeds of all structure in the universe. Regions that were slightly denser had slightly more gravity. They pulled on surrounding matter. They grew. Over time, the dense regions got denser. Matter fell into them, and they became denser still. This is gravitational instability. It's how structure forms. But here's the problem. For normal matter, this process is slow, really slow, because normal matter interacts with light. In the early universe, the normal matter was hot. It was a plasma of protons, electrons, and photons, all interacting, and pressure from radiation pushed back against gravity. This pressure prevented normal matter from clumping quickly. It slowed down the growth of structure. If the universe were only made of normal matter, the tiny fluctuations from the early universe wouldn't have had enough time to grow into galaxies and stars by now. The universe is only about 14 billion years old. That's not enough time for normal matter alone to form the structures we see. But dark matter changes everything. Dark matter doesn't interact with light. It doesn't feel radiation pressure. In the early universe, when normal matter was stuck in a hot plasma, dark matter was already free, already able to clump, already responding to gravity without interference. Dark matter started collapsing into structures long before normal matter could. It formed a framework, a scaffolding, filaments and halos of dark matter that grew and became denser. And then, once the universe cooled enough for normal matter to decouple from radiation, about 380,000 years after the Big Bang, the normal matter fell into the gravitational wells created by dark matter. Normal matter followed the dark matter. It gathered in the places where dark matter had already accumulated. And this is how galaxies formed. Normal matter fell into dark matter halos and formed stars. The visible galaxies we see are nestled inside massive halos of dark matter. The dark matter provides the gravitational framework. The normal matter is just the visible filling, and this process continues today. Dark matter halos are still the scaffolding. Galaxies are still held together by dark matter. When galaxies collide and merge, their dark matter halos merge too. The large-scale structure of the universe, the cosmic web with its filaments and voids, is primarily a dark matter structure. The galaxies are just tracers, lighting up where the dark matter is. Without dark matter, there's no scaffolding, no framework for structure to form quickly enough, no galaxies, no stars, no planets, no us. Dark matter is essential. It's not optional. It's the hidden architecture of the cosmos. And we live in a universe built on this invisible foundation. Let me give you a more personal sense of what this means, because I want you to really feel the strangeness of dark matter. Right now, as you're hearing these words, dark matter particles are passing through you, billions of them. Every second, they're coming from all directions, from above, from below, from the sides. They pass through the earth like it's not even there. They pass through every atom in your body without interacting, without bouncing off anything, without leaving a trace. You're sitting in a sea of dark matter particles. The Milky Way has a dark matter halo that extends far beyond the visible disk of stars. We're inside that halo. The solar system is moving through dark matter. The Earth is moving through dark matter. You are moving through dark matter, and dark matter is moving through you. But you don't feel it. You can't detect it with your senses. It's completely invisible to you. And yet, it's there, right now, this moment, as real as the air you breathe, but completely undetectable without sophisticated equipment. And even with that equipment, we still haven't caught it. Think about how strange that is. Most of the matter in the galaxy, most of the mass that holds the galaxy together, is made of something we cannot see or feel, something that flows through us constantly, something that's been there your whole life without you ever knowing it. You've been surrounded by dark matter since the day you were born, since before humans existed, since the Earth formed, since the galaxy formed. Dark matter was here first. It created the framework that allowed galaxies to form. It's older than stars, older than the atoms in your body, and it's invisible. This should fundamentally change how you think about reality, because reality is not what it appears to be. The universe you can see, the solid matter you can touch, the light you can perceive, all of it is a tiny fraction of what's actually there. Most of existence is hidden from you, operating on principles you can't directly observe, affecting the universe in ways that are only visible through their consequences. You're living in a cosmos where what you cannot see is more important than what you can see, where the invisible scaffolding is what allows the visible universe to exist. And that's profound. That should make you pause and reconsider what you think you know about the world. Now let me explain something else that's crucial for understanding dark matter, because there's often confusion between dark matter and dark energy, and they're completely different things. Dark matter is matter. It has mass, it has gravity, it pulls things together, it clumps, it forms halos around galaxies, it creates structure. Dark energy, on the other hand, is something completely different. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. It's a property of space itself, as far as we can tell. It pushes things apart. It causes the universe to expand faster and faster. Dark energy makes up about 68% of the universe. Add that to the 27% that's dark matter and the 5% that's normal matter, and you get 100%. The entire universe. But dark energy is not dark matter. They're separate things, separate mysteries, and they have opposite effects. Dark matter pulls. It creates gravity. It holds things together. Dark energy pushes. It causes expansion. It drives things apart. Both are called dark because we don't know what they are, because they're invisible. But that's where the similarity ends. Tonight, we're focused on dark matter, the stuff that holds galaxies together. But I wanted to make sure you understand that these are different phenomena, different unsolved mysteries, both telling us that we don't understand the universe as well as we thought. Now, why haven't we detected dark matter particles yet? If dark matter is passing through us constantly, if it's everywhere, why haven't we found it? The answer is that we've been trying. For decades, we've built incredibly sensitive detectors. We've put them deep underground to shield them from cosmic rays and other background radiation. We've cooled them to near absolute zero to detect the tiniest energy deposits. We're looking for WIMPs colliding with atomic nuclei. When a WIMP hits a nucleus, it should transfer a tiny amount of energy. The nucleus recoils, and we try to detect that recoil. It would be an extremely rare event. You might get 1 collision per month in a ton of detector material, maybe less. It's like trying to find a needle in a haystack the size of a planet. But we're looking. Multiple experiments, xenon, lux, CDMS, and others, all using different techniques, all trying to catch that 1 collision. So far, nothing definitive. There have been some hints, some anomalies, but nothing that holds up to scrutiny, nothing that can't be explained by background noise or cosmic rays or radioactive contamination. The particles, if they're WIMPs, are interacting even more weakly than we thought. Or maybe they're not WIMPs at all. Maybe they're axions or some other particle, and we need different detection strategies. This is why the search continues, why new experiments are being built, why physicists are trying different approaches, because dark matter is out there. We know it from its gravitational effects. We just need to figure out how to detect it directly. And when we do, when we finally catch a dark matter particle, it will be one of the greatest discoveries in physics. It will tell us what most of the universe is made of. It will reveal a new type of matter, a new fundamental particle. It will probably require new physics, new theories beyond the standard model, and it will open up questions we haven't even thought of yet. This is the exciting part, not knowing, searching, working to solve one of the biggest mysteries in science, and we're getting closer. The experiments are getting more sensitive. The theories are getting more refined. Someday, maybe soon, we'll find it. And when we do, it will change everything. Let me also tell you about how dark matter affects the fate of the universe, because it's not just important for how things are now, but for how things will be in the future. The universe is expanding. This has been known since the 1920s, when Edwin Hubble observed that distant galaxies are moving away from us. The farther away they are, the faster they're receding. This expansion is driven by dark energy, which is causing it to accelerate. But dark matter plays a role too. Dark matter has gravity. It pulls things together. It resists expansion. For a long time, cosmologists thought the expansion of the universe would eventually slow down due to gravity. Maybe it would stop. Maybe it would reverse, and the universe would collapse in a big crunch. This depended on the density of matter. If there was enough matter, enough gravity, expansion would reverse. If there wasn't enough, expansion would continue forever. Dark matter was part of this calculation. It contributed to the total density. It added gravity to slow the expansion. But then, in the late 1990s, astronomers discovered that the expansion is accelerating, not slowing down. Dark energy is pushing harder than gravity is pulling. This was a shock. It won the Nobel Prize, and it means the universe's fate is different from what we thought. The expansion will continue forever, accelerating. Galaxies will move away from each other faster and faster. Eventually, distant galaxies will be receding faster than the speed of light, not through space, but because space between us and them is expanding so fast. Their light will never reach us. They'll disappear beyond the cosmic horizon. And This has already started. There are galaxies so far away that their light, emitted now, will never reach us because space is expanding too fast. In the far future, the universe will be a lonely place. Galaxies in our local group bound together by gravity will remain, but everything else will be gone. The sky will be dark. Other galaxies will have disappeared, and trillions of years from now, if any civilizations still exist, they'll look out and see almost nothing, just their own galaxy or cluster. The rest of the universe will be beyond reach. This is the fate dictated by dark energy. But dark matter is still important. It's what keeps galaxies together. Without dark matter, even the local group might not hold together. Dark matter is the glue, and in the far future, dark matter halos around galaxies will be all that keeps stars from drifting apart. So, dark matter doesn't determine the ultimate fate of the universe. That's dark energy's role, but it does determine the structure of what remains. It's essential for anything to exist at all, and that makes it crucial for understanding not just the present, but the long-term future of the cosmos. Let me bring this back to something even more fundamental, because understanding dark matter teaches us something important about science itself, about knowledge, about how we come to understand reality. We've discovered dark matter through indirect observations. We've never seen it, never touched it, never detected a single particle, and yet we're confident it exists. Why? Because we've measured its effects. We've seen how it influences things we can observe, and from those influences, we've inferred its presence. This is how science often works. We observe effects, we measure phenomena, and we build models to explain what we see. Sometimes those models require things we can't directly observe. Atoms were like this once. In the 1800s, scientists inferred that matter was made of atoms because of chemical reactions and properties of gases. But no one had seen an atom. They were too small. Atoms were a theoretical construct, a model that explained observations. It wasn't until the early 1900s that direct evidence for atoms emerged, and it wasn't until electron microscopes were developed that we could actually image individual atoms. For decades, atoms were invisible, but they were real. Dark matter is similar. We can't see it directly, but its effects are real. Its gravitational influence is measurable, and from those measurements, we build models. We infer properties. We predict what should happen in different situations. And when those predictions are confirmed, when multiple independent observations all point to the same thing, we become confident, not certain. Science is never certain, but confident. This is the nature of scientific knowledge. It's provisional. It's based on evidence. It's revised as new data comes in. And it's humble. Scientists are comfortable saying, "We don't know." We don't know what dark matter is. We have ideas. We have candidates. But we don't know for sure, and that's okay. That's how science is supposed to work. You acknowledge uncertainty. You search for answers. You build better experiments. You test hypotheses. And gradually, over time, understanding deepens. This is the process, and dark matter is one of the great unsolved problems. One of the frontiers where we're actively working to understand. It's exciting, it's humbling, And it reminds us that no matter how much we've learned, there's always more to discover. The universe is full of mysteries, and dark matter is one of the biggest. Now, I want to take you deeper into the historical journey of accepting dark matter, because it's a fascinating story of how science works, how paradigm shifts happen, and how difficult it is to overturn established thinking. When Fritz Zwicky first proposed dark matter in 1933, he was dismissed, not because his observations were wrong, but because the conclusion was too radical. The idea that most of the universe's mass is invisible, made of something completely different from everything we know, that was too much, too strange. Scientists preferred to think Zwicky had made a mistake. Maybe his distance measurements were off. Maybe the galaxies weren't actually moving as fast as he thought. Maybe there was some other explanation. Any other explanation seemed more plausible than invisible matter dominating the cosmos. This is human nature. We resist ideas that challenge our worldview. We prefer explanations that fit with what we already believe. And in the 1930s, the idea that everything we could see was just a tiny fraction of what existed, that was impossible to accept. So Zwicky's work was largely ignored for decades, cited occasionally but not taken seriously. It wasn't until Vera Rubin's work in the 70s that the scientific community had to confront the evidence. But even then, it took time. Rubin published her first papers on galaxy rotation curves in the late 70s and early 80s. She showed clearly that galaxies were rotating wrong, that the rotation curves were flat instead of declining, that this required extra mass, dark matter. But there was still resistance. Some scientists looked for other explanations. Maybe our understanding of gravity was wrong on galactic scales. Maybe Newton's laws and Einstein's relativity didn't apply to galaxies the same way they apply to solar systems. This led to theories like pondered, modified Newtonian dynamics, proposed by Mordechai Milgram in 1983. Pondered suggested that gravity works differently when accelerations are very low, as they are in the outer regions of galaxies. If you modify the laws of gravity slightly, you can explain the rotation curves without dark matter, and this was attractive to some because it didn't require inventing new invisible matter. It just required adjusting existing physics. But MOND had problems. It worked for galaxy rotation curves, kind of, but it didn't work for galaxy clusters. It didn't explain the coma cluster. It didn't fit cosmological observations. And when the bullet cluster was observed in 2006, showing clear separation between visible matter and the location of most mass, MOND couldn't explain it. You needed dark matter, real, actual matter, not just modified gravity. By the 2000s, the evidence for dark matter had become overwhelming. Rotation curves, galaxy clusters, gravitational lensing, the cosmic microwave background, large-scale structure, every observation pointed to the same conclusion. There's invisible matter, lots of it. It's not regular matter, it's something else. And the scientific community accepted it. Not unanimously. There are still holdouts, still researchers exploring modified gravity theories, but the mainstream consensus is clear. Dark matter is real. This journey from Zwicky's initial observation to widespread acceptance took about 70 years. 70 years for a revolutionary idea to be accepted. That might seem slow, but it's actually how science works. New ideas are treated skeptically. They should be. Extraordinary claims require extraordinary evidence, and dark matter was an extraordinary claim. But the evidence accumulated from multiple independent sources, using different methods, all pointing to the same thing. And eventually, the weight of evidence became undeniable. This is the process. This is how scientific revolutions happen, not overnight, not easily, but through gradual accumulation of evidence until the old paradigm can no longer explain observations and a new paradigm must be accepted. Let me also tell you about one of the most beautiful aspects of dark matter, the cosmic web, because this shows dark matter's role in creating the large-scale structure of the universe. When you map out where galaxies are, when you create three-dimensional maps of the universe, showing the positions of millions of galaxies, a pattern emerges. Galaxies aren't randomly distributed. They're organized into structures, long filaments, vast walls, enormous clusters where filaments meet, and between them, voids, huge empty regions with almost no galaxies. This is called the cosmic web, and it looks like, well, a web, a vast network of filaments connecting clusters with voids in between. It's one of the most striking patterns in nature, visible on the largest scales imaginable, spanning billions of light years. And this structure is created by dark matter. Here's how it works. In the early universe, dark matter had tiny fluctuations in density. Some regions were slightly denser than others. These overdense regions had stronger gravity. They pulled in more dark matter. They grew. As they grew, they pulled in even more matter. This is positive feedback, gravitational instability. The rich get richer. Dense regions become denser. Underdense regions lose matter to the overdense regions and become voids. And the dark matter doesn't just collapse into spheres. It collapses along certain directions. It forms filaments, sheets, walls. These connect the overdense regions, and where filaments intersect, you get clusters, massive concentrations of dark matter. This dark matter structure forms first, before galaxies, before stars. It creates a scaffolding, a framework, and then normal matter falls into this framework. Gas follows the dark matter. It flows along the filaments. It accumulates in the high-density regions, and there it forms stars and galaxies. Galaxies light up where the dark matter is. They're tracers of the dark matter structure. So when we map galaxies and see the cosmic web, what we're really seeing is the dark matter web, the underlying structure, lit up by stars and galaxies that formed in its densest regions. Simulations of structure formation running on supercomputers can recreate this. You start with tiny fluctuations in dark matter density. You let gravity do its work over billions of years. And out comes the cosmic web, filaments, clusters, voids, matching observations incredibly well. Without dark matter, these simulations don't work. Without the gravitational pull of dark matter forming structure early, before normal matter could, you don't get the cosmic web. You don't get galaxies forming in the right places at the right times. The structure we observe requires dark matter. It's beautiful, and it's further confirmation that dark matter is real, that it's essential, that it's the hidden architecture underlying everything we see. Now let me tell you something that might make your head spin, because when we talk about dark matter halos around galaxies, the scales involved are enormous. The Milky Way's visible disk, the part with stars that we can see, is about 100,000 light-years across. That's already huge, but the dark matter halo extends far beyond that. The dark matter halo is roughly spherical, though slightly flattened, and it extends out to at least 600,000 light-years, maybe more. We're not sure exactly where it ends because it gets less dense farther out and becomes hard to measure, but it's at least 6 times larger than the visible galaxy. 6 times. And most of the galaxy's mass is in that halo. The stars, the gas, the dust, all the visible matter is about 1/6 of the total mass. The other 5/6 is dark matter in the halo. We're sitting inside this halo. The solar system is about 26,000 light-years from the galactic center. We're well inside the dark matter halo, surrounded by it, moving through it as we orbit the galaxy. The solar system takes about 230 million years to complete one orbit around the galactic center, and that orbit is influenced by both visible and dark matter. The dark matter contributes to the gravitational pull, keeping us in orbit. Without it, the galaxy would be much less massive. The orbital speeds would be different. The structure would be different. Dark matter is not just around the galaxy, it's in the galaxy. It permeates it. There's dark matter here, in the solar system, passing through the Earth constantly. And throughout the galaxy, there's a smooth halo of dark matter, providing the gravitational backbone. Other galaxies have similar halos. Andromeda, our nearest large neighbor, has a dark matter halo. So does every galaxy. When galaxies collide, their dark matter halos merge. Simulations show this. The Milky Way and Andromeda are going to collide in about 4 billion years. Their dark matter halos will merge into a larger halo. The visible galaxies will merge too, forming a large elliptical galaxy. But the dark matter halos will play a crucial role. They'll interact gravitationally. They'll influence how the collision unfolds. Even though dark matter is invisible and doesn't interact electromagnetically, its gravitational effects are profound. It shapes galaxies. It determines their masses. It influences their evolution. And it's everywhere. You can't escape it. Every galaxy is embedded in dark matter. Every cluster of galaxies is held together by dark matter. The cosmic web is a dark matter structure. Dark matter is ubiquitous. It's the background of the universe, and we're just now beginning to understand its role. Let me share one more perspective that I find deeply meaningful, because dark matter teaches us something important about the limits of human perception and the nature of reality. For all of human history, until the 20th century, we thought we could see the universe. We thought that what was visible was what existed. Stars, planets, moons, comets, nebulae. These were the universe. We didn't know about galaxies until the 1920s. We didn't know the universe was expanding until the 1920s. We didn't know about dark matter until the 1970s, when we finally accepted it. Our understanding of the cosmos has been revolutionized in just the last century. And dark matter is one of the biggest revelations. It tells us that our senses deceive us, that what we can see is not representative of what exists, that reality is far stranger than appearances suggest. This is humbling. It should be humbling. We've discovered that we're blind to most of the universe, that we're missing most of what's there, that our intuitions, built from everyday experience with visible matter, don't apply to the cosmos at large. And this raises questions. What else are we missing? What else exists that we can't detect? Dark matter took 70 years to be accepted, even with clear evidence. What evidence are we ignoring now? What paradigm shifts await us? We don't know. We can't know. But history teaches us that the universe is always more complex, more surprising than we think, that every answer raises new questions, that every discovery reveals new mysteries. Dark matter is one of those mysteries. We know it exists, we know it's important, but we don't know what it is. And that not knowing is exciting. It's the frontier. It's where science is happening. It's where we're pushing the boundaries of knowledge. And it reminds us that we're at the beginning of understanding, not the end. The universe is vast, complex, full of phenomena we haven't discovered yet. Dark matter is just one example, and there will be more. There always are. Before I transition to what comes next in our understanding, let me make sure you appreciate the sheer magnitude of what dark matter represents for physics and cosmology. We have a standard model of particle physics that describes all known particles and forces: quarks, leptons, gauge bosons, the electromagnetic force, the weak nuclear force, the strong nuclear force. It's one of the most successful theories in science. It predicts phenomena to incredible precision. The magnetic moment of the electron calculated to 12 decimal places. The masses of particles predicted before they're discovered. It's beautiful. It works, but it's incomplete. And dark matter is one of the clearest pieces of evidence that it's incomplete. The standard model doesn't include dark matter. There's no particle in the standard model that could be dark matter. The particles we know about are all too light, too short-lived, or interact too strongly to be dark matter. Dark matter requires something new, something beyond the standard model. And this is exciting for particle physicists, because it means there's new physics to discover, new particles, possibly new forces, definitely new phenomena. The standard model has been so successful that some physicists worried we were running out of things to discover, that we understood everything at the fundamental level. But dark matter says no. There's more. There's a whole sector of particles and maybe forces that we haven't discovered yet. And this is driving research. Experiments at the Large Hadron Collider looking for supersymmetric particles, underground detectors searching for WIMPs, axion experiments. All of these are motivated by dark matter, by the fact that we know something is out there and we need to find it. And when we do, it will be revolutionary. It will extend the standard model. It will give us a more complete picture of particle physics. It might even point the way to unifying forces, to understanding quantum gravity, to answering questions about why the universe is the way it is. Dark matter is not just a curiosity. It's a window into new physics, into deeper understanding, and that's why so much effort is going into finding it. That's why scientists are devoting their careers to this search. Because the payoff, when we finally detect dark matter particles, will be enormous. It will reshape physics. It will answer questions we've been asking for decades. And it will probably raise new questions we haven't thought of yet. That's how science progresses. Each answer leads to more questions. Each discovery reveals new frontiers. And dark matter is one of the great frontiers of 21st century physics. Now, let me also address something you might be wondering, because it's a common question. If dark matter doesn't interact with light, if it only interacts through gravity, how do we know it's not just black holes? Couldn't all the dark matter be black holes, which are dark and have gravity? This is a reasonable question, and scientists have considered it. Primordial black holes that formed in the early universe from density fluctuations, have been proposed as dark matter candidates. But we've ruled them out for most mass ranges. Here's why. Black holes bend light. If there were lots of black holes scattered throughout the galaxy's dark matter halo, they would act as gravitational lenses. When a black hole passes in front of a background star, the star's light is magnified and bent. The star brightens temporarily. This is called microlensing. Scientists have searched for these microlensing events. They've monitored millions of stars, looking for temporary brightening that could indicate a black hole passing in front. And they've found some events, but nowhere near enough to account for all the dark matter. The number of microlensing events tells us there aren't enough black holes in the halo to be the dark matter. There might be some, maybe a small fraction, but not all of it, not even most of it. There are also constraints from the cosmic microwave background. The early universe's radiation patterns are sensitive to the amount of normal matter that existed. Black holes are made of normal matter. They're formed from collapsed stars or from overdensities of normal matter. If there were enough black holes to be dark matter, it would affect the cosmic microwave background in ways we don't see. The data tells us that normal matter is only about 5% of the universe. Black holes, being normal matter, fall into that 5%. They can't be the dark matter. So, while black holes exist, and while some might be scattered throughout the galaxy, they're not the answer. Dark matter is something else, something truly exotic, something not made of protons, neutrons, and electrons. And that's what makes it so interesting and so challenging to detect. Let me bring this full circle by connecting dark matter back to you personally one more time, because I want you to walk away from this understanding how it touches your life, even though it's invisible. You exist because of dark matter. Let me explain what I mean. In the early universe, if there had been no dark matter, structure wouldn't have formed. Tiny density fluctuations wouldn't have grown into galaxies. Matter would have remained spread out, diffuse. Maybe small structures would have formed eventually, but not galaxies. not on the timescales we observe. Without galaxies forming when they did, where they did, stars wouldn't have formed in the right places. The chemistry of the universe would be different. Heavy elements might not have been produced in sufficient quantities. Supernovae, which produce elements heavier than iron, happen in galaxies. Without galaxies, no supernovae. Without supernovae, no heavy elements. Without heavy elements, no rocky planets. Without rocky planets, no place for life as we know it to evolve. The chain is clear. Dark matter enables galaxy formation. Galaxy formation enables star formation. Star formation enables element production. Element production enables planet formation. Planet formation enables life. You are the end result of a process that started with dark matter, creating the scaffolding for galaxies. The atoms in your body were forged, dashed in, stars that formed in galaxies that were held together by dark matter. You are, in a very real sense, a product of dark matter. Not directly. You're made of normal matter, but that normal matter exists in the configuration it does, forming planets and life, because of dark matter's role in structuring the universe. Without dark matter, you wouldn't be here. Neither would Earth, neither would the Sun, neither would the Milky Way. The universe would be a very different, probably lifeless place. So dark matter, invisible though it is essential for your existence. It's part of your cosmic heritage, part of the story of how you came to be, and that should change how you think about it. It's not just some abstract physics concept. It's part of the foundation of reality, part of what makes the universe capable of producing stars and planets and life, and that's profound. That's worth appreciating. That's worth understanding deeply. The distribution of dark matter follows patterns we can map. Through gravitational lensing studies of thousands of galaxy clusters, astronomers have reconstructed three-dimensional maps of dark matter. These maps reveal structure. Dark matter isn't uniformly distributed. It clumps, forms filaments, creates the cosmic web. Galaxies sit at the nodes where filaments intersect. Like cities along highways, the dark matter filaments came first, formed from tiny density fluctuations in the early universe. Gravity amplified these fluctuations. Dense regions attracted more matter, became denser. Less dense regions lost matter, became voids. Over billions of years, this process created the structure we observe. Long filaments of dark matter stretching across hundreds of millions of light years, connecting galaxy clusters with vast voids between them. And normal matter, gas primarily, fell into these dark matter structures, condensed, formed stars, built galaxies. The visible universe traces the invisible scaffolding. We can see this in simulations, computer models that start with dark matter distributed almost uniformly with tiny fluctuations. Let gravity operate, watch structure emerge. The simulations match observations remarkably well. The distribution of galaxies, the sizes of clusters, the shapes of filaments, all predicted by models that include dark matter. These simulations couldn't produce the observed structure without dark matter. With only normal matter, Structure formation is too slow, too inefficient. By the time you get significant clumping, the universe has expanded too much. Galaxies forming today instead of billions of years ago. This doesn't match observations, but add dark matter. Let it collapse first. Create gravitational wells. Then normal matter falls in. Rapid structure formation. Galaxies form early. Matches what we see. The cosmic web is dark matter's signature, its fingerprint on the universe. Dwarf galaxies provide crucial tests. These small galaxies, containing millions rather than billions of stars, have very high dark matter fractions. Some are almost entirely dark matter, 99% dark matter by mass, only 1% normal matter. These galaxies challenge formation theories. How did they form? Why do they have so much dark matter relative to normal matter? One hypothesis involves tidal stripping. Maybe they were once larger galaxies that passed near massive neighbors. Tidal forces stripped away normal matter, which interacts and can be removed. But dark matter, collisionless, stayed bound. This would leave behind dark matter-dominated remnants. Another idea involves feedback from star formation. Supernovae and stellar winds can blow normal matter out of small galaxies. Weak gravity can't hold it, but dark matter, unaffected by such processes, remains. This creates high dark matter fractions. Studying dwarf galaxies constrains dark matter properties. If dark matter particles can interact with each other, even weakly, it affects dwarf galaxy structure. Self-interacting dark matter would thermalize, create cores instead of the cusps predicted by collisionless dark matter. Observations are mixed. Some dwarf galaxies have cores, some have cusps, might indicate diverse formation histories. Or it might indicate dark matter has small but non-zero self-interaction. This is actively researched. Simulations with different dark matter models, comparing to observations, trying to distinguish between formation effects and fundamental particle properties. Warm dark matter versus cold dark matter changes predictions. Cold dark matter moves slowly compared to light speed. It can clump on all scales, small and large. Warm dark matter moves faster. It can't clump on small scales. Motion smooths out small structures. This affects predictions. Cold dark matter predicts lots of small dark matter halos. Dwarf galaxies. Satellite galaxies around larger galaxies. Warm dark matter predicts fewer. Observations show the Milky Way has dozens of satellite galaxies. Models predict hundreds or thousands depending on assumptions. This is the missing satellites problem. Where are all the small dark matter halos? Several solutions exist. Maybe they're there, but starless. Pure dark matter with no visible galaxies. Hard to detect. Or maybe feedback from the first stars, heated gas, prevented it from condensing into small galaxies. This suppresses satellite formation without changing dark matter properties. Or maybe dark matter is warm. Fewer small halos predicted. Matches observations better. Distinguishing these scenarios requires better observations. Fainter satellite detections. more detailed simulations. Progress is happening. Surveys finding ultra-faint dwarf galaxies, some so faint they contain only thousands of stars. Each discovery refines our understanding of structure on small scales, tests dark matter models. Direct detection experiments use multiple strategies. Cryogenic detectors cool to millikelvin temperatures, detect phonons, vibrations in crystal lattices from recoiling nuclei. CDMS uses germanium and silicon crystals. Super CDMS improves sensitivity, measures both phonons and ionization, distinguishes signal from background. Liquid noble gas detectors use xenon or argon. WIMP collides with nucleus, produces scintillation light and ionization electrons. Measure both. Discriminate between nuclear recoils, potential WIMPs, and electron recoils, background radiation. Xenon and Lux collaborations use multi-ton xenon detectors, deep underground in Italy and South Dakota respectively, shielded from cosmic rays, from radioactive contamination, every component ultra-pure. Years of data collection, no definitive signals yet, but constraints tighten. If WIMPs exist in certain mass and interaction ranges, we'd have seen them. Those ranges are excluded. Directionality experiments aim to detect the direction of incoming particles. Dark matter should come preferentially from one direction as Earth moves through the dark matter halo. Detecting directionality would confirm detection is genuine dark matter, not background. These experiments use gas detectors, track recoiling nuclei paths. Technically challenging, but promising. Indirect detection searches for dark matter annihilation products. If dark matter particles encounter each other, they might annihilate, produce normal particles, photons, neutrinos, antimatter. These might be detectable. Gamma-ray telescopes search for excess photons from galactic center or dwarf galaxies, places where dark matter density is high. Fermi Large Area Telescope has found some anomalies. Excess gamma rays near galactic center could be dark matter annihilation, or could be unresolved pulsars, or something else, not conclusive. Neutrino telescopes, like IceCube, search for neutrinos from dark matter annihilation in the Sun. Dark matter might accumulate in the Sun's core, annihilate, produce neutrinos that escape. Detection would indicate dark matter, nothing definitive yet. Antimatter searches use detectors like AMS on the International Space Station. Measure cosmic ray composition. Look for excess positrons or antiprotons that could come from dark matter annihilation. Some excesses observed, interpretations debated. Could be dark matter, could be pulsars producing antimatter, could be other astrophysical sources. Distinguishing requires more data, better understanding of backgrounds. Collider searches look for dark matter production. If dark matter particles interact through forces accessible at colliders, they might be created. Large Hadron Collider smashes protons together at enormous energies, creates showers of particles. If dark matter is produced, it wouldn't be detected directly. would carry away energy and momentum invisibly. Signature is missing energy. Events where measured energy and momentum don't balance. Some missing, carried off by invisible particles. This happens with neutrinos. Also would happen with dark matter. LHC searches for such events, looks for patterns consistent with supersymmetric particles or other dark matter candidates. No discoveries yet, but excludes parameter space. If certain supersymmetric particles existed, they'd have been produced. We'd have seen them. They don't exist in those forms. The search continues at higher energies. Future colliders might reach energy scales where dark matter becomes accessible. Primordial black holes in certain mass ranges remain viable dark matter candidates, not stellar mass black holes. Those are excluded, but black holes formed in the early universe from density fluctuations. Before stars existed, certain mass windows aren't fully excluded. Asteroid mass primordial black holes, or larger planet mass. These could be dark matter. Current observations haven't ruled them out completely. Searches continue. Microlensing surveys looking for lensing events with specific durations indicating specific masses. Gravitational. Wave observatories might detect mergers of primordial black holes if they exist in sufficient numbers. The detection of gravitational waves from black hole mergers has renewed interest. Some mergers involve black holes with masses unexpected from stellar evolution. Could some be primordial? Possibly. Not confirmed. But intriguing. More data needed. Future gravitational wave detectors will probe wider mass ranges. Test primordial black hole scenarios more thoroughly. Self-interacting dark matter models address certain discrepancies. Standard cold dark matter is collisionless. Particles pass through each other. No interactions. This predicts cuspy density profiles in galaxy centers. Dense cores. Observations sometimes show flatter cores instead, especially in dwarf galaxies. Self-interacting dark matter would allow particles to scatter off each other, transfers momentum, thermalizes, creates cores. If the interaction strength is tuned correctly, it can match observations. Not too strong, or it would affect large-scale structure. Not too weak, or it wouldn't solve the core cusp problem. Just right. Goldilocks zone. Some models propose dark matter has its own force, a dark force, mediating interactions between dark matter particles, analogous to electromagnetism for charged particles. This would make dark matter more complex than a single collisionless particle. A sector of dark particles with interactions, hidden from us but affecting each other. This is speculative, but motivates searches for dark photons or other dark force carriers. Experiments look for mixing between dark photons and regular photons, rare transitions that would produce detectable signals. The role of dark matter in galaxy formation is nuanced. Simulations show dark matter halos form first, collapse under gravity, become denser. Normal matter, mostly hydrogen and helium gas, falls into these halos, concentrates at the centers where dark matter density is highest. Gas collides, unlike dark matter, loses energy through radiation, cools, settles into rotating disks. Within these disks, gas becomes dense enough to form stars. stars form galaxies. This process, hierarchical structure formation, explains why galaxies exist where they do, why they have the sizes and masses they do. Dark matter sets the stage. Without it, gas wouldn't have concentrated enough to form galaxies efficiently. But dark matter isn't enough alone. Feedback processes matter. Supernovae inject energy, heat gas, drive winds, prevent some gas from forming stars. Black hole feedback at galactic centers affects gas dynamics, regulates star formation. The interplay between dark matter, gravity pulling gas in, and feedback pushing gas out determines galaxy properties: mass, size, star formation rate, morphology. Understanding this requires sophisticated simulations including dark matter, gas dynamics, star formation, supernovae, black holes, all coupled together. Modern simulations reproduce observed galaxy populations fairly well, but details are challenging. Small-scale structure, satellite galaxies, central black hole masses, all constrain both dark matter properties and feedback physics. Disentangling effects is difficult. The Milky Way's dark matter halo extends far beyond visible stars. Stars are concentrated in a disk about 100,000 light-years across, but the dark matter halo extends at least several 100,000 light-years, maybe farther. The Sun orbits within this halo. Dark matter density near the solar system is estimated at about 0.3 protons per cubic centimeter in terms of mass density. That's incredibly sparse, near vacuum by everyday standards, but integrated over the halo's volume, it's enormous, dominates the galaxy's mass, affects the Sun's orbit, affects everything. The local dark matter density is important for direct detection experiments. Higher density means more dark matter particles passing through detectors. Better chances of detection. Measuring this density isn't direct. We infer it from galaxy models, from stellar motions, from rotation curve fits. Different methods give slightly different values. Uncertainties of factors of 2. This translates to uncertainties in expected detection rates. Makes direct detection more challenging. You don't know exactly how many particles should hit your detector, just rough estimates. Velocity distribution of dark matter particles matters too. Are they all moving at similar speeds? Broad distribution? Streams? The standard assumption is a Maxwell-Boltzmann distribution. Particles in thermal equilibrium. This is probably an approximation. The halo formed from mergers, accretion of smaller halos. These processes create substructure, streams of dark matter on specific orbits. Dark matter flowing through the galaxy in coherent streams from disrupted satellite galaxies. Detecting such streams would affect direct detection signals, might create annual modulation as Earth's motion through the halo varies. Some experiments claim to see annual modulation. Dharma, Libra, has long reported signals varying with season, consistent with dark matter, but other experiments don't confirm. Interpretations are controversial. If real, what kind of dark matter produces this signal? Doesn't match WIMPs in standard scenarios? Requires unusual properties. Most physicists are skeptical, think it's a systematic effect, not dark matter, but it's unresolved. Ongoing debate. Dark matter in galaxy clusters is detected primarily through gravitational lensing. Clusters are massive. Dark matter dominates. Total mass bends light from background galaxies, creates arcs, multiple images, strong lensing when alignment is good, weak lensing when shear effects are subtle. Measured statistically across many background galaxies. By mapping lensing, astronomers reconstruct cluster mass distributions. Find where dark matter is. Compare to where normal matter is. Hot gas emitting X-rays. Galaxies. The gas is easy to map with X-ray telescopes. Contains most normal matter in clusters, much more than in galaxies. Maybe 80% of cluster normal matter is hot gas. Dark matter distribution extends beyond gas, more diffuse, but also shows clumps. Substructure. Clusters aren't smooth, they're messy, result of mergers. Smaller clusters colliding, producing complex mass distributions. Studying these maps tests dark matter models. Cold dark matter predicts certain substructure statistics, amount of clumping on various scales. Observations constrain these predictions, generally match, but tensions exist. Small discrepancies possibly indicating dark matter properties or incomplete understanding of cluster physics. The formation of the first stars relied on dark matter. In the early universe, after recombination when atoms formed and light could travel freely, matter was almost uniformly distributed. Tiny density fluctuations existed. Quantum fluctuations from inflation stretched to cosmic scales. These fluctuations were small, 1 part in 100,000. Normal matter in this state couldn't collapse quickly. Radiation pressure and gas pressure resisted collapse, but dark matter, immune to radiation pressure, started collapsing immediately. Dark matter halos formed, grew, became denser. Normal matter fell into these halos, concentrated, eventually reached densities where it could cool and collapse further. Form the first stars. Population 3 stars, made entirely of hydrogen and helium. No heavy elements. These stars were massive, hundreds of solar masses, lived fast, died young in supernovae, enriched the universe with first heavy elements. This process happened within dark matter halos. Without dark matter, the timeline changes. First stars form much later, maybe not at all in quantities needed. Dark matter accelerated structure formation, made the universe interesting earlier, allowed complexity to develop on timescales compatible with observations. Dark matter halos have profiles, descriptions of how density varies with distance from center. The Navarro-Frenk-White profile is standard. Predicts density decreasing as 1 over radius in the outer regions, and rising steeply towards center, proportional to 1 over radius squared or steeper. This creates a cusp, very high central densities. Simulations produce NFW profiles naturally from cold, dark matter, but observations, especially of dwarf galaxies and low surface brightness galaxies, sometimes show cores, flatter central density profiles. This is the core cusp problem. Multiple proposed solutions, baryonic feedback, supernovae and stellar winds pushing gas around, transferring energy to dark matter gravitationally, flattening the central density, self-interacting dark matter as mentioned earlier, or different dark matter physics, warm dark matter, fuzzy dark matter with wave-like properties on small scales. All these affect predicted profiles. Distinguishing them requires precise observations and detailed simulations. Ongoing effort. Fuzzy dark matter is an alternative to WIMPs. Proposes dark matter is ultralight bosons. Mass around 10 to the minus 22 electron volts. Incredibly light. These particles have large quantum wavelengths. The de Broglie wavelength is inversely proportional to mass. Ultralight particles have wavelengths of kiloparsecs, thousands of light years. On these scales, quantum effects matter. The dark matter behaves like a wave, a field, rather than particles. This suppresses small-scale structure naturally, avoids the missing satellites problem, and creates solitonic cores in halos. Quantum pressure preventing infinite densities at centers. Observations might distinguish fuzzy dark matter from cold dark matter through halo profiles and substructure statistics. Current data don't strongly favor either, but upcoming observations, more sensitive measurements of galaxy density profiles might decide. Fuzzy dark matter is theoretically motivated by string theory. Axions in some scenarios have ultralight masses, making fuzzy dark matter a prediction of certain beyond standard model theories. Testing it tests those theories. Cosmological simulations of dark matter require immense computational resources. Billions of particles, each representing a clump of dark matter, gravity calculated between all particles, time steps of millions of years, evolved over billions of years of cosmic history, requires supercomputers, months of computation time. The largest simulations track dark matter in volumes hundreds of millions of light-years on a side. Resolve halos down to millions of solar masses. Capture a dynamic range of billions, from cosmic web filaments to dwarf galaxies. These simulations predict halo mass functions. How many halos exist at each mass? Spatial correlation functions, how halos cluster, merger rates, how often halos merge, all testable against observations. So far, predictions match reasonably well, some tensions as mentioned, but overall, cold dark matter plus dark energy, the lambda CDM model, fits data impressively. This is the standard cosmological model. Dark matter is central to it. Remove dark matter, the model breaks. Can't fit observations? This is additional confirmation dark matter exists. Not just one observation, but the entire cosmological framework requires it. The density of dark matter changes through cosmic history. In the early universe, matter and radiation were both important. As the universe expanded, their densities decreased, but at different rates. Radiation density decreases faster than matter density. Because radiation is redshifted, wavelengths stretch. Energy per photon decreases. Matter just dilutes, doesn't lose energy. So there was a transition. matter radiation equality when matter density equaled radiation density. After this, matter dominated. Dark matter dominated actually, since it's most of matter. This transition affected structure formation. Before equality, dark matter tried to collapse, but radiation pressure in the coupled photon-baryon fluid prevented normal matter from collapsing. Dark matter could collapse, but normal matter couldn't join until after recombination. This created a head start for dark matter. By the time normal matter could collapse freely, dark matter halos were already forming. This explains why dark matter distributions are smoother than normal matter distributions on some scales. Dark matter collapsed first, slowly. Normal matter fell in later, more rapidly, creating denser concentrations. These historical details are encoded in cosmic microwave background patterns, precisely measured by satellites like WMAP and Planck. The data confirm dark matter existed and dominated the early universe. Another independent line of evidence: dark matter might decay. Unstable dark matter with lifetimes longer than the age of the universe would appear stable now, but might decay eventually. Decay products would include normal particles. Photons, perhaps, detectable. Searches look for monoenergetic photon lines from dark matter decay. Specific energies corresponding to dark matter particle mass. None found convincingly. This constrains decay rates. If dark matter decays, it does so slowly. Lifetime much longer than the universe's age. Otherwise, we'd see signals, or dark matter is truly stable, which most models assume. Stability often comes from symmetries, conservation laws forbidding decay. In supersymmetric models, our parity conservation makes the lightest supersymmetric particle stable. It can't decay because there's nothing lighter with the same quantum numbers. Similar mechanisms could stabilize other dark matter candidates. Stability is important. If dark matter decayed quickly, its density would decrease. Structure formation would be affected. Observations constraining dark matter density over cosmic time indirectly constrain decay rates. Caustic structures might form in dark matter distributions. When dark matter streams intersect, they create caustics. Regions where density is enhanced, not infinite because particles have velocities, but significantly higher than surroundings. These caustics could be detectable through lensing, through enhanced annihilation signals if dark matter annihilates. Some researchers have searched for caustics. Results are debated, not universally accepted. If real, caustics would probe dark matter phase space distribution, how velocities correlate with positions. More detailed structure than just density profiles. This is frontier research. Theoretical predictions exist. Observational confirmation is challenging. Annual modulation signatures are expected from Earth's motion. Earth orbits the Sun orbits the galaxy, moving through the dark matter halo. Earth's velocity relative to the halo varies seasonally. In June, Earth's orbital motion adds to the Sun's motion, higher relative velocity. In December, Earth's orbital motion subtracts, lower relative velocity. Higher velocity means more dark matter particles encountered. higher detection rates expected. This creates annual modulation. Peak in June, minimum in December. A few percent variation. Dharma/Libra claims to see this. Others don't. CoGNT reported hints, later retracted. CDMS saw nothing. Xenon saw nothing. Either Dharma/Libra is seeing dark matter with unusual properties, or it's a systematic effect. The community leans toward systematic, but mysteries remain. Resolving this requires more experiments, better understanding of backgrounds, careful cross-checks. Neutron stars might capture dark matter. High densities in neutron star cores allow dark matter accumulation. Dark matter particles passing through lose energy through scattering off nucleons. Get captured, sink to center, accumulate. If enough accumulates, annihilation increases. Heats the neutron star. Observations of old cold neutron stars constrain dark matter interactions. If interaction were too strong, too much dark matter would be captured. Too much heating. Neutron stars would be warmer than observed. They're not. So interaction is weak. This constrains WIMP properties. Interaction cross-sections. Masses. Complementary to direct detection experiments. Different method. Different systematic uncertainties. Together, they narrow parameter space. Brown dwarfs and exoplanets might be affected by dark matter. Capture and annihilation could provide internal heating, making brown dwarfs slightly warmer than expected from their own contraction and cooling. No clear evidence yet, but future infrared surveys might detect anomalies. Similarly, dark matter annihilation inside planets could contribute to internal heat. Earth's core temperature might have contributions from dark matter, almost certainly negligible, but in principle testable. Exotic scenarios, unlikely to be significant, but illustrative of how dark matter interacts or doesn't with everything. The observational evidence for dark matter is diverse and redundant. Rotation curves, cluster dynamics, gravitational lensing, cosmic microwave background, large-scale structure, abundances of light elements from Big Bang nucleosynthesis requiring low baryon density. All these independent observations point to dark matter. This redundancy is important. If one observation were anomalous, we might suspect error. But when 10 different methods all agree, confidence increases. Dark matter is real, not a mistake, not a misinterpretation, a fundamental component of the universe, and this motivates the intense effort to detect it directly, to understand what it is, because knowing the universe's composition is central to understanding reality. The technological innovations driven by dark matter research benefit society broadly. Developing ultra-sensitive detectors requires advancing many technologies. Cryogenics, low-noise electronics, ultra-pure materials, radiation shielding. These technologies find applications beyond dark matter searches. Medical imaging improves from detector advances. Material science benefits from purity requirements. Computing algorithms developed for analyzing massive datasets apply to other fields. Machine learning techniques trained on dark matter simulations transfer to climate modeling, financial analysis, medical diagnostics. The investments in fundamental research generate spillover benefits. Not immediately, not directly, but consistently. History shows this pattern. Quantum mechanics was pure science. Now it underpins semiconductors, lasers, MRI machines. General relativity was abstract theory. Now it's essential for GPS. Dark matter research continues this tradition, pursuing knowledge for its own sake while inadvertently creating useful technologies and techniques. The sociology of dark matter research illustrates how science addresses uncertainty. No one knows what dark matter is. Many theories compete. Researchers advocate for their preferred candidates. Design experiments testing specific hypotheses. This creates healthy competition, different groups pursuing different strategies. If one succeeds, everyone learns. If all fail, we eliminate possibilities, narrow the search. This is how science progresses through uncertainty, not waiting for perfect knowledge, but exploring actively, testing ideas, learning from failures, adjusting theories based on evidence. The dark matter community collaborates despite competition. Data is shared, results published openly, null results reported honestly. This openness accelerates progress, prevents duplication of effort, ensures mistakes are caught. It's a model for addressing difficult problems, transparency, collaboration, rigorous testing, honest reporting even when results disappoint. The funding challenges for long-term dark matter searches reflect societal priorities. Experiments run for decades. Exenon began in 2005, still operating, no detection yet. Funders grow impatient, want results, tangible outcomes, but dark matter might be incredibly hard to detect, might require even longer searches, bigger detectors, more time. Convincing funding agencies and governments to maintain support is difficult, requires demonstrating progress, showing improved sensitivity, explaining why continued investment is worthwhile even without detection. Scientists make the case that eliminating parameter space is progress, that constraining dark matter properties is valuable even if the particle remains elusive, and that the technology development and training of scientists justifies cost. Mostly, funding continues, but not guaranteed. Political changes affect priorities. Economic downturns strain budgets. Long-term experiments are vulnerable. This tension between open-ended research and accountability is inherent to science, managed through communication, through demonstrating value, through patience. The education and outreach around dark matter reaches millions. Documentaries explain the mystery. Planetarium shows visualize simulations. Science museums feature dark matter exhibits. YouTube videos and podcasts discuss latest results. This public engagement serves multiple purposes. It educates, inspires young people to pursue science, builds support for research funding by demonstrating why it matters, and it satisfies curiosity. People want to know what the universe is made of. Dark matter is accessible enough that non-specialists can understand the question and appreciate the mystery. This democratizes knowledge, makes cutting-edge physics available to everyone, and it creates feedback. Public interest encourages scientists, validates the importance of the work, creates a constituency supporting continued research. The international nature of dark matter research fosters cooperation. Experiments in Italy, the US, China, Japan, Canada. Theorists worldwide. Collaborations span continents. Data shared across borders. This cooperation transcends political tensions. Scientists from countries with strained diplomatic relations work together on detectors. This is science at its best, united by curiosity, by shared goals, by commitment to understanding nature. The collaborations build connections between cultures, between nations, create networks of mutual respect and communication. This might seem tangential to dark matter itself, but it's part of the broader impact. Science as a force for cooperation, for finding common ground, for working toward shared understanding. Alternative theories to dark matter continue to be explored. Modified gravity theories like MOND have evolved. TVES, tensor vector scalar gravity, attempts to make MOND relativistic, compatible with cosmology. It has problems, doesn't fit all observations, but research continues. Some scientists believe dark matter is too convenient, too ad hoc, adding invisible stuff to make equations work. They prefer modifying laws instead. This skepticism is healthy. Science needs challenges, needs people questioning assumptions, testing alternatives. Most evidence favors dark matter, but alternatives shouldn't be dismissed without fair consideration. The scientific process accommodates dissent, encourages testing competing ideas. Let's evidence decide. So far, evidence favors dark matter strongly. But modified gravity isn't completely ruled out, might apply in certain regimes, might require both dark matter and modified gravity. Unlikely, but possible. Keeping open minds while following evidence is the scientific way. The connection between dark matter and cosmic inflation is speculative but intriguing. Inflation is the hypothesized rapid expansion in the universe's first moments. It explains why the universe is so uniform, why it's flat, why no magnetic monopoles are observed. During inflation, quantum fluctuations were stretched to cosmic scales. These became the density fluctuations that seeded structure. Dark matter amplified these fluctuations through gravity, but inflation might also have produced dark matter itself. Certain inflation fields driving inflation, might decay into dark matter particles. This would explain dark matter's abundance, why it has the density observed. The details depend on the inflation model. Many exist. Not all predict dark matter production, but some do. Connecting inflation and dark matter would be elegant. Two mysteries addressing each other. Inflation creates dark matter. Dark matter creates structure. A coherent cosmological story. Testing this requires better understanding of both inflation and dark matter. Difficult, but motivates theoretical work. The multiverse interpretation raises questions about dark matter. If multiple universes exist with different physical constants, dark matter properties might vary. Some universes might have more dark matter, some less, some none. The amount of dark matter affects structure formation, affects galaxy formation, affects whether stars and planets and life can exist. Too much dark matter, structure forms too early, collapses into black holes. Too little, structure doesn't form. No galaxies. Either way, no observers. So universes we observe must have dark matter in the right range. This is anthropic reasoning, controversial. Some find it explanatory, others find it defeatist, avoiding the question of why our universe has specific properties by appealing to selection effects. Whether dark matter admits anthropic explanation depends on whether multiverse exists, whether dark matter properties vary between universes. Both unknown, but interesting to consider, highlights how finely balanced the universe seems, how special the conditions permitting complexity are. Dark matter's role in future cosmic evolution is predictable. As the universe continues expanding, accelerated by dark energy, structures become more isolated. Galaxy clusters remain gravitationally bound, but clusters separate from each other. Eventually, trillions of years from now, distant clusters recede beyond causal contact. Dark matter in our local group holds it together. Milky Way and Andromeda merge, form a giant elliptical. Other local group members are absorbed. This merged galaxy persists. Dark matter halo maintains it. But beyond, the universe empties. Dark energy dominates more. Expansion accelerates more. Eventually, even galaxies might be torn apart. Big Rip scenario: if dark energy strengthens, everything disintegrates. Dark matter can't prevent it if expansion is strong enough. Or maybe dark energy remains constant. Heat death. Universe expands forever. Cools. Dark matter remains, clumped in galactic remnants. Cold. Dark. Unchanging for eternity. Either scenario, dark matter's role diminishes over time. Structure exists now, will exist for trillions of years. But eventually, change ceases. Entropy maximizes. Dark matter becomes irrelevant. Relic of a more energetic era. The psychological impact of dark matter knowledge varies. Some find it unsettling. Most of reality is invisible, unknown, beyond our grasp. This is uncomfortable, challenges the feeling of understanding the world. Others find it exhilarating. There's so much to discover, so much mystery. The universe is bigger and stranger than we thought. Both reactions are valid. Dark matter does challenge our cosmic self-perception. We're not just small in space. We're interacting with only a fraction of what exists. Our senses and tools miss most of reality. This is profound, philosophically significant, and how we respond reveals our relationship with uncertainty and mystery. Science embraces mystery, sees it as opportunity, seeks to illuminate darkness with knowledge. This attitude, applied broadly, is valuable. Accepting what we don't know, working to find out, staying curious, remaining humble. The comparison to historical scientific mysteries is instructive. Before atoms were accepted, matter's ultimate composition was mysterious. People speculated. Democritus proposed atoms in ancient Greece, but no proof. For millennia, the idea languished. Then evidence accumulated. Chemical reactions followed patterns. Brownian motion suggested discrete particles. Eventually, atoms were accepted, detected, understood. Dark matter is similar. We're in the phase before direct detection. Evidence is strong. Indirect observations compel belief. But the smoking gun, direct detection, awaits. When it comes, dark matter will transition from mystery to known component of reality, just as atoms did, just as microbes did before microscopes, just as viruses did before electron microscopes. Science repeatedly encounters invisible phenomena, infers their existence from effects, eventually develops tools to detect them directly. Dark matter follows this pattern, and history suggests will eventually succeed. The integration of dark matter into culture happens gradually. Science fiction incorporates it. TV shows and movies reference dark matter, usually incorrectly, treating it as magic or energy source. But the cultural penetration is real. Dark matter enters public consciousness, becomes part of how people think about the universe. This isn't immediate. Took decades for relativity to penetrate culture, generations for evolution. But dark matter is getting there, and as it does, it changes baseline understanding. People grow up knowing most of the universe is invisible. This shapes worldviews, affects how future generations approach science and mystery. Cultural integration of scientific knowledge matters. It makes society more scientifically literate, better equipped to make informed decisions, better able to appreciate the cosmos. The ethics of dark matter research are generally uncontroversial. Unlike genetic engineering or AI, dark matter detection doesn't raise moral dilemmas. It's pure science, understanding nature. No one is harmed, no ethical lines crossed. This simplicity is rare in modern science. Many fields face ethical complexities. Dark matter research doesn't. The worst outcome is wasted resources if we never detect it. Even then, technological and intellectual benefits might justify cost. So, funding dark matter research is ethically straightforward. It's about priorities, allocating resources between competing goods. But no fundamental moral objections arise. This freedom allows scientists to focus on science, not ethics committees or public controversy, a luxury, an advantage, and it means public support can be built on pure curiosity and knowledge-seeking. Noble motives broadly endorsed. The potential for paradigm shift if dark matter is detected is enormous. Currently, dark matter is inferred, not observed directly. If we detect the particle, everything changes. We know what it is, can study its properties, mass, interaction strengths, decay modes, if any. This might reveal new forces, new symmetries, new principles of physics, could point toward grand unification, toward quantum gravity, toward string theory or alternatives. The standard model would expand, new particles added, maybe new forces. Textbooks would be rewritten, courses updated, a generation of physicists would work on implications, testing predictions, exploring consequences. It would be like discovering the neutron, or quarks, or the Higgs boson, except bigger, because dark matter is most of the universe. Understanding it is fundamental, central to cosmology and particle physics. The impact would ripple through multiple fields: astronomy, physics, philosophy, cosmology, science communication, a milestone in human knowledge, comparable to discovering DNA structure, or confirming the Big Bang, or detecting gravitational waves. Transformative. The cross-disciplinary nature of dark matter research is notable. Astronomers observe galaxies, map structure. Particle physicists build detectors, develop theories. Cosmologists run simulations, model evolution. Nuclear physicists understand detector backgrounds. Material scientists create ultra-pure substances. Engineers design cryogenic systems. Computer scientists analyze data with algorithms. Statisticians quantify significance. All collaborating, all contributing. This synthesis is modern science at work. No single discipline solves dark matter, requires expertise from many fields, and this cross-pollination benefits everyone. Astronomers learn particle physics, particle physicists learn astrophysics. Ideas transfer, techniques combine, new hybrid fields emerge. Dark matter astrophysics, astroparticle physics. These fields didn't exist decades ago. They emerged from the dark matter problem, bringing communities together. This pattern repeats across science. Complex problems require diverse expertise. Collaboration across disciplines becomes essential. Dark matter exemplifies this beautifully. The role of serendipity in potential dark matter discovery shouldn't be underestimated. Many scientific breakthroughs were accidental. Penicillin, discovered by contamination. Cosmic microwave background found while troubleshooting antenna noise. X-rays discovered during unrelated experiments. Dark matter might be similar, might be detected in an experiment designed for something else. A collider searching for supersymmetry finds a different dark matter candidate. An astrophysical survey finds an unexpected signal. A neutrino detector sees something anomalous. Science prepares for expected discoveries while remaining open to unexpected ones. Flexibility matters. Curiosity matters. Following leads even when they don't match predictions. This openness to surprise drives progress. Dark matter might be discovered deliberately by an experiment designed specifically to find it, or it might be stumbled upon. Either way, the prepared mind recognizes its significance. The next generation of experiments will probe previously inaccessible parameter space. Xenon TET and LZ are scaling up liquid xenon detectors, multi-ton targets, lower backgrounds, better sensitivity. Super CDMS Snow Lab in Canada uses improved technology, colder, cleaner, more channels. These experiments will reach sensitivities where they detect neutrino backgrounds, solar neutrinos, atmospheric neutrinos. This creates a flaw. Below this sensitivity, neutrinos mimic dark matter signals. Becomes harder to distinguish, requires different strategies. Directionality becomes essential. Determining particle directions separates dark matter from neutrinos. Dark matter comes from galactic halo, specific directions. Neutrinos come isotropically or from the sun. Different angular distributions. Experiments developing directional capability face challenges. Lower sensitivity, larger detectors needed. Trade-offs between directional information and event rates. But worth pursuing. The only way forward once neutrino floor is reached. The theoretical landscape for dark matter is vast. Hundreds of models proposed, each with different particles, different interactions, different predictions. This diversity reflects our ignorance. We don't know enough to narrow to one theory. So many remain viable. As experimental constraints tighten, parameter space shrinks. Some models get excluded, others remain. Eventually, hopefully, only one survives, matches all observations, makes testable predictions, gets confirmed. This process takes time, decades. But it's how science works. Explore many ideas, test rigorously, eliminate what doesn't work, converge on truth. Dark matter theory is in the exploration phase. Many options, few ruled out, much parameter space remaining. Future experiments will accelerate elimination, narrow possibilities, guide theoretical development. The complementarity between different search strategies is crucial. Direct detection probes local dark matter density. Collider searches probe whether dark matter can be produced at accessible energies. Indirect detection probes whether dark matter annihilates or decays. Astrophysical observations probe dark matter's role in structure formation. All these approaches constrain different aspects. A particle could evade one search but be accessible to another. WIMPs might interact too weakly for direct detection but might be produced at colliders, or vice versa. Axions wouldn't be produced at colliders but might be detected by axion haloscopes. This complementarity means failure of one experiment doesn't doom the search, just redirects effort, and success in any channel confirms dark matter, provides clues guiding others. So, the multi-pronged approach is strategic, increases chances of success, provides cross-checks. The human stories behind dark matter research are compelling. Vera Rubin faced barriers as a woman in science, persevered, made groundbreaking discoveries, changed our understanding of the universe. Her legacy extends beyond dark matter, inspired generations of women astronomers, showed that barriers can be overcome, that talent and determination matter more than gender. Graduate students spend years building detectors underground, living near remote sites, enduring isolation, debugging equipment, analyzing data, hoping for detection that might never come. Their dedication drives progress. Postdocs and early career researchers bet their careers on dark matter, publish null results, maintain enthusiasm despite lack of detection. This perseverance is admirable, necessary. Science rewards those who persist, who believe in the importance of the question even when answers elude us. The philosophical questions dark matter raises touch fundamental issues. What is real? Is reality limited to what we directly observe? Or do we infer existence from indirect effects and trust our reasoning? Dark matter forces us toward the second position. We can't see it, can't touch it, can't detect it with our senses or even most instruments. But we trust that it exists because the gravitational evidence is overwhelming. This is an epistemological stance. Knowledge comes not just from direct observation, but from inference, from models that explain observations. This is how much of science works. We don't see atoms, we infer them. Don't see electrons in wires. Infer their motion from current. Don't see magnetic fields. Infer them from forces on magnets. Dark matter is an extreme case. Most of the universe inferred, not observed. But it's continuous with how science has always operated, trusting that the universe is comprehensible, that effects have causes, that careful observation and reasoning reveal truths about reality even when reality is hidden. The economic impact of dark matter research is modest but real. Thousands of scientists employed, graduate students trained, equipment purchased, facilities built and maintained. This circulates money through economies, creates jobs, supports industries. Detector components are manufactured, electronics produced, cryogenic systems installed. Mining companies provide ultra-pure materials. All economic activity, modest compared to total economy, but non-zero, and the trained scientists contribute beyond dark matter, apply skills to other problems, industry, academia, government. The training infrastructure for physicists benefits society broadly. Not all trained in dark matter research stay in the field. Many transition to finance, technology, data science, medicine, taking analytical skills with them. So the investment in dark matter research pays dividends beyond direct discoveries. Through human capital development, through maintaining scientific infrastructure, through technological spin-offs. The aesthetic dimension of dark matter shouldn't be overlooked. Images of galaxy clusters with lensing arcs are beautiful, scientifically informative, but also artistically striking. Simulations of the cosmic web are visually stunning. Filaments of dark matter creating intricate patterns across hundreds of millions of light years. This beauty is part of why people care about cosmology, why the public supports research, why students enter the field. Beauty motivates, inspires wonder, creates emotional connection to science. Dark matter contributes to this. The idea that invisible scaffolding holds galaxies together is poetic, that most of the universe is hidden, that we're surrounded by mystery. This resonates emotionally, not just intellectually, and emotional engagement matters. It sustains interest, maintains curiosity, makes science feel meaningful rather than dry technical work. The legacy we leave for future generations includes dark matter knowledge. What we discover now, or fail to discover, shapes what future scientists work on. If we detect dark matter soon, they'll study its properties, implications, applications if any. If we don't, they'll continue searching. With better technology, different approaches. Either way, the question passes forward. Each generation builds on the previous, adds knowledge, refines tools, asks deeper questions. This continuity across generations is how science progresses. No single person solves dark matter, no single generation likely, but collectively, over time, through cumulative effort, answers emerge. We're part of that process, contributing our piece, advancing the frontier slightly, leaving it better than we found it, for those who come after, who will continue the work, who will eventually, hopefully, solve this mystery and move on to the next. The philosophical implications are profound. Most of the universe is invisible. We see a small fraction: atoms, light, the electromagnetic spectrum. This is what our senses evolved to detect, what our instruments are designed to observe. But it's not most of reality. Most of reality is dark, invisible to our tools and senses. This is humbling, reminds us how limited our perspective is, how much exists beyond our perception, and it's exciting. There's more to discover, more to understand. The universe is richer and stranger than it appears. Dark matter is part of this, a major part, and solving the dark matter mystery will expand our understanding enormously, will show us what the universe is really made of, will reveal a hidden sector of physics. That's worth pursuing, worth the decades of effort, worth the billions spent on experiments. Because understanding the cosmos is understanding our place in it, and dark matter is key to that understanding. Thank you for exploring the invisible universe with me, and remember that most of what exists is hidden from direct observation. Yet, through careful measurement, brilliant deduction, and patient observation of gravitational effects, we've mapped the unseeable scaffolding that holds galaxies together and makes our existence possible.